Remember, Grant, everyone's hearing what you're saying now.
Grant said which guy was the sigma?
Cody, they can hear you too. Okay, so like I said, we are talking about differential equations. Differential equations is referring to when we are going to be integrating a lot. So instead of saying y is equal to x, we're always going to have something in the form of dy over dx. That's why we call them differential equations, because we have the derivative and we need to solve by going backwards. All right? Now, let's go ahead and just try this one out first. The first thing, when we do this, if we want to find all functions that satisfy dy over dx equals 3x squared plus cosine x, well, the reason we say all functions is because what are we missing when we take the integral? We're missing c. So what we need to do is, when we take the integral, we just need to add the c, and doing that shows that we have multiple functions, not just one function. We have 3x squared plus cosine x plus 1 plus 2 plus 3 plus 0.5 plus e plus pi and so on and so forth. So let's go ahead and just take the integral. Remember, when you take the integral of a derivative, what happens to the two? They are going to cancel. They undo each other. Taking the derivative and then taking the integral just leaves you with your original function. So this is equal to the integral of 3x squared plus cosine of x. Obviously, to do the integral, all we need to do is anti-differentiate. So then, in order to do this, remember, we're going to be kind of learning new rules, and it's going to be very intuitive what we do. So a lot of the times, sometimes you will have to take a derivative or take the integral and then take the derivative of your answer in order to double check. Oh, was I correct? Yes or no? So if we do this, we are going to get that y, because remember, the integral undoes the dy dx and just leaves us with y, is equal to, what is the antiderivative of 3x squared?
X
Caleb? X cubed.
Yeah.
And then what is the antiderivative of cosine x? Sine x. And then, when you're doing trig, if you do not have them fully memorized, and even if you do, always just take the derivative again to double check if it's positive or negative. Because remember, the derivative of sine is cosine, but the derivative of cosine is negative sine. So what's the derivative of sine? Cosine, positive cosine. The derivative of sine is positive cosine. Therefore, this should be just plus. And then what am I missing from here? Now I have to add
C.
Plus c plus that constant. Just remember, this disappears when taking the derivative. I'm also super excited for this unit because remember all those equations we used last year, like the logistic function, those weird exponential functions, the Newton's law of cooling. Do you remember those a little bit?
No.
I don't think advanced algebra did that.
You should have done Newton's law of cooling. Like the T, like the temperature, like if a cup of coffee sits out for a while, what's the temperature after a certain amount of time? We will actually, and I know this sounds exciting, so don't get too excited, we will create those formulas using calculus.
No.
We're actually going to develop them.
Freaking way.
I know, right?
Shut
Wow.
the front door.
I know, wow. That's not okay to say, Rowan. Come on. Wow. Okay, now, let's go ahead and do initial value problems. Recall that many functions all have the same derivative, so additional information is necessary to specify.
Sorry, I was just wondering if they knew about the pictures or if you knew that juniors have pictures right now.
On the list, it does not tell me that we have it right now.
Okay, well, all the juniors, the other two classes are going to take pictures right now, and we just came from Mr. Beagle's room, so we were wondering if we could get the other juniors so we could all take a class picture.
Yes, you may. Don't you?
You should come with us.
I unfortunately can't. We have the seniors here.
Just like everyone, like. What do you mean, unfortunately? Seniors can like take this.
Well, I can't leave y'all.
It's okay.
This is awkward. Okay.
Yeah, you can leave. It's fine.
Faith has already taught our class before.
Oh yeah.
There you go. Oh, that's true. Okay. So initial value problems. when we have initial value problems, it is just going to be, well, what do we want to find? We want to find R.
Wait, sorry.
No.
I have a question.
Yep.
Should we wait and we can do like a senior bonding activity? 'Cause, like,
Wait, you're
most
so
of the
right.
class is
Oh my
gone.
god.
Oh,
You don't want to, you don't
Yeah,
want
they
to.
don't want to get behind.
fine. Well, the video is going to be awkward for Isaac and Nebby to watch.
You
But I'll just
pause
tell them to skip through the video. Sure. What do y'all want to do? Y'all have some free time. What do you want to do?
I don't know. Let's just all stand up.
Just
Yeah,
all
I think-
stand
I
up.
think that's a good plan.
Just why?
Yeah.
Would we like to go on a walk outside?
Yes.
All right.
That should be fun.
We're going on a walk outside. One second. Let me make sure I have my keys.
You can forget those.
Yeah, that's fine.
That's fine.
We can walk it out. It's fine.
Isaac, hi, Abby. Sorry, we just took a walk outside.
Wait, can I tell them what happened?
Yeah, sure, go ahead.
Okay, Isaac and Evie. So basically, we went outside and we showed Mr. Holm all of our cars, and then we all squeezed into Lincoln's car.
It was
Yeah,
fun.
it was fun.
Hey guys, this is a terminal velocity face reveal, guys. This is math.
This is math. Okay, let's go over the initial value problem. All right. Now, with our integrals, as I said, we have a plus c. However, a lot of the times, just like with, if we remember point, slope, and derivatives, even though there's an infinite number of derivatives, correct? We know that we can find a value if we're given a point. So that is exactly what we're going to do now. So let's go ahead and start by writing this out and trying to get to a form of y equals. So I'm going to write this out as the integral from e squared minus 3x dx, and then we integrate this. Oh, sorry, e to the 2x minus 3x. And then the second portion is pretty simple. We just use the reverse power rule. But whenever you have an e or something like this, a good idea is to take the derivative to find out what the integral is. So what is the derivative of e to the 2x?
2e to the 2x.
2e to the 2x, right? So therefore, if we undo it, if we have e to the 2x, if we go the other way, instead of multiplying by 2, we would want to divide by 2. So we would get e to the 2x over 2. What we did here is we undid the chain rule. Minus 3x squared divided by 2, which we call the reverse power rule. Now, undoing the chain rule is something you're going to have to be doing quite a bit of. So make sure that as we progress further and further, you're understanding, okay, the derivative of this means I multiply on the outside by 2, therefore doing the integral means I divide by 2. Taking the derivative will not always work because it actually changes, such as sine and cosine, but it will give you little hints as to what does work and does not work. And then what do we have to add at the end? Plus c, which is going to be our constant or initial value. That is our constant. Okay? Now what do we do? Well, we have an x and a y, correct? Y equals this equation. We have x's here, and we have the point at 1/1/2. So I can state that since y equals this, 1/2 is equal to e to the 2 times 1 minus 3 times 1 squared over 2 plus c. Or I get 1/2 equals e squared minus 3 halves plus c. Therefore, c is equal to, I'm going to go ahead and move these all over to get 2 minus e squared. Oh, and I forgot my apologies, everybody. Divide by 2 here. Therefore, my equation, my specific equation that goes through these points is y equals e to the 2x divided by 2 minus 3x squared plus 2 minus e squared divided by 2. All right, do we have any questions on this portion here? Savannah?
Wait, so why do we change the square on like the 3x but not the e? But like we both divide them by the exact
Oh,
same.
because this is e squared, this is x squared times 3. So therefore when I input the 1, it's 1 squared, not 3 squared. Because am I squaring 3 here?
I mean, like, why did we add the square root on the x there and not changing
Which
the thing?
square root?
Like, why did, because it's, the normal equation is e to the 2x minus 3x. Why did we change it to 3x squared, but not changing it
Because
to
we
the
did
other?
the reverse power rule, right? What's the derivative of e to the x?
E to the x.
E to the x. And the derivative of e to the 2x is e to the 2x over 2. 2 times e to the x. Because we did two different rules here. Here we undid the chain rule and used the fact that the derivative of e to the x is the e to the x, and therefore the integral of e to the x is e to the x. Here we use the reverse power rule, where you add 1 to the power and then divide by that number. Okay? All right. Now, everybody go ahead and turn over to slope fields exploration. Here we have a general solution of the differential equation dy over dx equals cosine of x. Okay? So, I want you to look here and see, does this look like a cosine x graph though? No, what kind of graph does it look like? It looks like a bunch of what? Sine graphs, because where do we start at? We start at? And cosine always starts at 1. So, really, the cosine graph is here. Like this. So what is this graph representing? Well, this graph right here is representing our slopes. So, if we consider it, let's go ahead and look at the question. Since cosine x equals 0 at odd multiplicities of pi over 2, we should see that dy over dx equals 0 at odd multiplicities of pi over 2 on the graph. Is that true? And how can you tell? Well, let's look at this graph right here. What is happening at pi over 2 and 3 pi over 2? All of these go by pi over 2, by the way. So this would be pi over 2, pi, 3 pi over 2, and then 2 pi. So what happens at pi over 2 according to this graph? What do we get? We get a? What does that look like? There's a special name for it. It starts with an M. It is a maximum. So if we get a maximum, well, what is dy over dx equal to? 0. And what happens when a derivative equals 0? The original function has a maximum. So therefore, at pi over 2, we have a max. And what is happening at 3 pi over 2? We have a...
Isn't it a 0 instead of maximum?
What was that?
If there's a maximum in the derivative graph, doesn't that mean it's a 0 for the original graph?
No, it's the other way around. If there is a 0 in the derivative, that means that the original graph has a maximum, right? So right here, what this is graphing right now, this is, we have dy over dx equals cosine x, right? But what is the graph we're graphing? Sine of x. We just don't know which sine of x, because it could be sine of x plus 1, plus 2, plus 3. So all of these are sine of x, right? Correct? So if the derivative equals 0, that means we have a minimum or a maximum. And is that true here? Yes, because look at what we just graphed. What is cosine of x here? 0. Therefore, we have a maximum. We have a derivative here. Therefore, cosine is a minimum. So sine is a minimum. Algebraically, the y-coordinate does not affect the value of dy over dx equals cosine x. Can anyone tell me why not? Why does the y-coordinate not affect the value of dy over dx equals cosine x? We've answered this because what happens when you have a constant and we take the derivative of it? Cancels. Taking the derivative will cancel that out. Okay. Welcome back, y'all. We had fun.
So much fun.
They put me in the front row. I don't understand.
Usually they put the
Taller
short
though. Always so tall.
It's true.
Oh.
Hey, y'all. Come on in, quiet down.
Where'd y'all go?
We just went outside for a
We're
minute.
in Lincoln's Club.
Into Lincoln's car. Yeah.
Side quest.
Okay, everybody. So go ahead and turn here to the exploration, seeing the slopes. I'm going to go ahead and do a quick recap, so make sure you listen up. Right here, we are graphing right here, the derivative is equal to cosine of x. Well, what's the integral of cosine x? Sine x. So right here are all the possible sine graphs that we have. Okay? So, if we know that cosine equals 0, what do we know about sine of x? What do we know about the actual function? It's going to have either minimums or maximums. So that means every pi over 2, we're going to have a minimum. And then, whenever we have pi over 2 in any form, so pi over 2, 3 over 2, 5 over 2, we're going to have a minimum or a maximum because we know that the derivative is equal to 0. Does the y-coordinate affect the value of dy over dx equals cosine x? No, because when we take the derivative of a constant, what happens? The derivative makes it equal 0. So cosine of x could be the answer to any of these derivatives. So if we take the derivative of any of these functions up here, it could always be equal to just cosine x. Does the graph show that the y-coordinate does not affect the value of dy over dx? How can you tell? So looking at this graph, does the that constant c affect any of the? Does a constant c affect this graph at all? For the y value, though. Yeah, because what happens? We have how many graphs do we have here? Technically, an infinite number of graphs. So although the y value does not affect the x, it does affect the y. So that c value will always affect how we move up and down. Okay? You can see it because of the vertical shifts. According to the differential equation, dy over dx equals cosine x, what should the slope of the solution curves when x equals 0? Can you see this in the graph? So when the solution curve, when x equals 0, what should our derivative be equal to? Well, if we look here, what does the slope look like right at 0? It looks like 1. It looks like it's 1. So therefore, what's the cosine of 0 also? 1. So this is going to be 1. And why is that? Well, because we know that y equals sine of x. Therefore, the sine of 0 is equal to, I'd say, we know that y equals sine of x.
Put a sign up. Walk away.
And has a slope close to 1 at 0. We know that if dy over dx equals cosine x, y has to equal sine of x of some form, and the slope will always be about 1 right at 0. According to the differential equation, dy over dx equals cosine x, what should the slope of the solution curve be when x equals pi? So let's look at x equals pi now. What does this look like right here? Not 1, but -1. Correct? This is true. -1, and yes. And why is that? Well, what is the cosine of pi equal to? -1. So we can use either the graph to tell us, oh, here we know what dy dx equals because we can kind of approximate what we see in the slope. Or we can evaluate at cosine. Cosine of pi is equal to -1 because the derivative is cosine. Yes, Dave?
I have a question. So, is this the graph of like the original function? And then cosine
Yes.
is the-
That's all the possible original functions.
Okay.
Okay. Since cosine x is an even function, the slope at any point should be the same as the slope as its reflection across the y-axis. Is this true, and how can you tell? trying to figure out what that's asking. Since cosine of x is an even function, the slope at any point should be the same as the slope at its reflection across the y-axis. Is this true? And how can you tell? Maybe talk it over with your partner, see if you can figure anything out. The homework for tonight, try it out if you can.
If you look at this
1 through 22
across the y-axis,
Some of them are really
Oh, no, cosine. We're doing cosine. Look at sine.
okay, but even with cosine,
Yeah, but even with cosine.
so I don't know.
Mr. Holmes,
Yep.
equals taken derivative will. Is that cancel?
Where?
You're right.
Oh, wait, the
Number
line.
2, or is that camel?
Yeah, I don't.
The
Where?
last word?
You're writing.
Oh, cancel. Yeah.
Cancel.
It's
Okay,
cancel.
cool.
Like if you're flipping it across, then it's gonna be the opposite.
Okay, I'm hearing some good answers. Does anyone want to state what they said? Luke?
No, because if you flip it across, it'll be going the opposite direction of what it was for cosine. Like if it at 0, it's the slope is 1, but if you flip that across the y-axis, then it would be -1.
Very nice. And do you see that in here as you go across? Okay, does anyone have a response to that?
I'm confused.
About what?
Yeah.
When you fold it over the y-axis, does it mean you're almost like folding it in half, right? Like a paper? And so they align with each other.
Yes, so this slope, as we go here, as we approach this way, we notice the slope is going to be this. So what this is saying is that the slope decreases here, correct? And the slope decreases here, correct? But remember, which direction are we always going in? Always going to the right. So therefore, this slope is going from here to here, here to here. But notice, do the slopes change at an even rate as we move along this way? Yes, they move at the same, they change at the same rate. That's why we see that. It's a little bit off there, Luke, what you said. But what we're really seeing is, okay, well, the slope should be going towards 0 and going towards 0. Do those slopes go towards 0? Yes. And yes. We can see that.
Are the same. So it is even.
It is even, yes. Cosine is an even function. The slope will be the same. Yep. Because if we look here, is the slope here, if we take the slope right here and right here, is that the same slope if we draw that line there? Yes, it is. Even though it might not necessarily look like it's hard to see that without graphing out cosine and saying, oh yeah, the slopes are the same as I go backwards. It's just that a lot of times we want to say it's not because they're going in different directions. Their values are changing. But we're going from down to up, we're going from down to up, and so on and so forth. So let's go ahead and turn back here for you juniors. I will, once we get finished with this section, I'm going to move up to the initial value. Y'all didn't miss too much. I'll explain what we went through and how we did it. But I'm going to spend the rest of the time talking about slope fields. Slope fields can be confusing. But what we're going to do is construct a slope field for the equation of dy over dx is equal to cosine x. So in order to do this, what we are going to do is we're going to go ahead and label this right here. We have we're going to create a table like so. And we're going to look at, okay, well, what y's can we input? We're not necessarily going to be doing a lot with y's. They might pop up on the homework. I want you to try those out if you can, but they might be a little bit too difficult.
Is that dy over dx?
Yes, so, which we just cancel. So let's go ahead and calculate this out at negative pi over 2, 0, pi over 2, and pi. When we make slope fields, we are just going to be graphing the slopes. We're going to calculate the derivative and graph that slope on the graph, and you'll see it'll actually graph the original function in a way. So What y values? Do I care about any of them? Is there a y over here anywhere? No, so it doesn't matter. We can just kind of cross those out. We're going to cross those out, put x's there, however you want to do that. But for dy over dx, what is the cosine of negative pi equal to? The cosine of negative pi is equal to
0.
negative 1. Okay? Now what I'm going to do is I'm going to go ahead and graph a slope of negative 1 over here at negative pi. I'm going to label this negative pi over 2, 0, pi over 2, and pi. So what does the slope of negative 1 look like? It looks like this. Just graph like that. And then we graph here and here. Unless you have a y over here, you will not actually need to change anything. If there's a y, these will be different. But here, there's no y, so we just graph the same thing. Because like I said, the plus c just moves it up and down. Now, what happens when we input pi over 2? We are going to get 0. And so I'm going to graph 0, 0, 0. A slope right there. What's the cosine of pi over 2? Or sorry, what's the cosine of 0, I mean?
1.
1. So therefore I'm going to graph a slope of 1, 1, 1, 1, and 1. Oh, do y'all see the shape that's kind of coming out now?
No way. It's a sign.
Then pi over 2 is going to be 0 again. So I'm going to graph 0, 0, 0, 0. Cosine of pi is also negative 1. So I'm going to graph here, here, and here. And as you can see, using these slope fields, we just created the original function just by graphing the slopes. And if I graph this out like this, from here to here, if I start here, and I go from here to here to here to here, we have the graph of sine just from the derivatives. Now, you don't have to graph the sine graph. That's just me showing you that. The slope fields are just used to show what all those derivative values are. All right, does that make sense? A little bit? Yes, no, maybe so? Okay, seniors, on what we covered today, how do we feel about slope fields and initial value? Thumbs up, thumbs sideways, thumbs down. Just seniors. Sideways, sideways, thumbs down. Thumbs sideways, thumbs down. Okay, so I want y'all to start on 1 through 22 odd, and I'll come around to answer questions. And I'm going to scroll up for all the juniors so you can see what we did while you were gone. Besides jumping in Lincoln's car and taking pictures. That was fun. Okay.
Oh, I should do that.
No.
No. No.
I don't have a picture of it on my phone for sure. Okay. Now, for juniors, for initial value, what we have here is when we take the integral, we're left with plus c. So what we want to do is find out what c is by getting a point, just like we've done with point slope. The first thing we have to do, though, is integrate. So I integrate e to the 2x, and I get e to the 2x over 2. Now, how did I get that? I undid the chain rule. When you take the derivative of e to the 2x, what happens? What do you multiply by? 2, right? E to the 2x, take the derivative of the inside, multiply it on the outside, times 2 on the outside. Therefore, this becomes divided by 2 to undo that. Because then if you take the derivative of this, what do you get? E to the 2x. You undo the chain rule. Then you just use the reverse power rule. Add 1 to the power, divide by whatever power that is. We get negative 3x squared over 2 plus our constant c. To calculate c, all we need to do is input 1 and 1/2. Since we know that this is dy over dx, this right here is y. So input 1/2 for y, input 1 for x, and then solve for c. Once you have calculated c, you can just go ahead and input it back with this original function here, and you will get your answer. Yes, Emma?
Do you equate it to 1/2 and not 1 because your 1/2 is your y value?
Yes, exactly. Because remember, when you take the derivative of dy over dx, what are you left with? Just y. Yes. Question?
Sorry, can you explain the reverse chain rule you did?
Sure. 1 second. Let me. Everyone say bye, Abby. Bye, Luke. Oh, sorry, bye, Luke. Bye, Abby. Bye, Isaac.
Bye.